So in order to overcome the effect of the channel length modulation, or in order to suppress the effect of channel length modulation, we have uh, seen the cascode current mirror circuit. Today we will see how exactly the cascode current mirror circuit is going to be generated, and for that we have to start with the basic current mirror circuit only. So this diagram, whatever I have shown here, this represents the basic current mirror circuit, right? And we have seen the equation for ID1 and ID2, which is the modified equation after having seen the effect of the channel length modulation here. And here the most important fact or factor is that your VDS1, the voltage between drain to source for the first transistor, is equal to, of course, VGS1, because it is a diode connected device. And since this point is common for both the transistor 1 and transistor 2, your VGS2 also happens to be same as VGS1, but the only problem is your VDS2. So your VDS2 need not necessarily be equal to the value of VDS1, because this is a different transistor, this is the different transistor. So if you want to keep your I out is equals to I reference, the variation or the deviation of VDS2 with respect to VDS1 will not allow you to properly or exactly copy the current from the reference source when you consider the effect of channel length modulation. If you do not consider the effect of channel length modulation, then the basic current mirror circuit will be okay. So now, in order to take care of the channel length modulation, right, we have to go with the cascode current mirror circuit. Now let us try to see how exactly we will be able to go with the working of the cascode current mirror circuit with this reference or this introduction as the background. Now, to suppress the effect of channel length modulation, I used it as CLM, channel length modulation. We use the cascode current source, and you can see I draw the diagram once again here. I have this circuit. All of you please copy down this again. So this is a diode connected device. If you have already done it, fine. I think up to here you had done it in your previous class. Now what I do here, for this up to here we had taken the basic current mirror circuit. Now what I will do here is I will add one more transistor or one more MOS device, to which this is my current source. I reference, this is of course VDD. Now let me take this point as P, and this is my I out. Now you can make out the difference between the diagram which I had drawn earlier and now. So what I have done here is I have included one more device. This is of course M1, this is M2, and this is now M3, and this voltage, let me call this as VB, and this potential I will call it as Y. This is referred to as Cascode current source. This is referred to as cascode current source. Now, see here, listen to me very carefully. This is the reference source. This is the device across which you have to maintain the current I out proportional to I reference, right? So now, because of the variation in the voltage of the device M2 and M1, the drain to source voltage of this M2 need not necessarily be equal to the drain to source voltage of M1. That is where you might have certain errors in copying this current to the output current here. So that is when we consider the effect of the channel length modulation. Now if you want to suppress the effect of channel length modulation, what I need to do here is I have considered one more device here, which is M3, right? So for Vx to be equal to Vy, that is what is my requirement, Vx to be equal to Vy. So as long as your Vx is equal to Vy, VDS1 will be equal to VDS2. So when VDS2 is equal to VDS1 here, then your channel length modulation effect will be suppressed, right? So that necessitates the voltage at this point Y should be equal to voltage at X. So assuming that the value of Vy is not equal to Vx, right? So now we have to compensate for that difference. That is done with the help of adding one more device here. So now I can write it here as Vy is equals to Vb minus VGS3. Look at your circuit and your network theory concepts. So this voltage Vy, okay, should be equal to Vb, this voltage, minus VGS3. You know what is VGS3? This is the value of VGS3. So for Vx is equals to Vy, you need the value of Vy to be equal to Vb minus VGX3, right? So here Vb is chosen in such a way that Vb is chosen in such a way that Vx is equals to Vy. So this will definitely make your I out equal to I reference. When Vx is equals to Vy, your I out is equals to I reference. So this is where you need to have the value of, or you need to have the cascode current sources, right? So the ID1 value will almost become equal to ID2 with high accuracy, using cascode current source. This is not the end of the cascode current source. Now we have to have Vb, or we have to choose Vb in such a way that Vx is equals to Vy. Now the question is how to generate or how to get Vb to ensure Vx is equals to Vy. How to generate Vb so that Vx is equals to Vy. how to generate VB so that Vx is equals to Vy. Now let me draw one more diagram here. I have I reference as usual, then I have two transistors connected in cascade. Please note that cascade is different and cascode is different. I have it something like this, and I will keep it as it is for the time being. Both are of course a diode connected transistors or the devices. So this is my I reference. This is of course VDD, and this device I call it as M0. This point is X. This device I call it as M1, and this point I call it as N. Now if I take this as plus and this as minus, let us see what exactly we are going to get here. All of you please copy down this circuit. Now we are in the process of how to generate VB, that is in the previous frame. I will go back to that frame, and this circuit or this arrangement is referred to as the cascode current source, modified to generate what? Bias voltage. Because we have to generate this voltage VB. This is called as the cascode current source modified to generate bias voltage. Now I am going back to this. Here once again I will write, what I will write is VB is equals to VGS3. Look from the diagram. VB is equals to VGS3 plus Vy. I hope all of you agree with me. This VB is also written as VGS3 plus Vx as long as you want to have Vy is equals to Vx, because our idea is to have Vx is equals to Vy or Vy is equals to Vx. So therefore your VB can also be written as VGS3 plus Vx, or your Vy is written as VB minus VGS3. Vy is written as VB minus VGS3. So the same thing I will write here also. VB is equals to VGS3 plus Vy, which is also equal to VGS3 plus Vx, or your Vy is equals to VB minus VGS3. It is for the previous frame. Now to ensure that Vx is equals to Vy, so I will write as VB is equals to VGS3 plus Vx. VB is equals to VGS3 plus Vx. This I have already written here, and once again I will write it. VB is equals to VGS3 plus Vx. I hope up to here it is very clear. So now if A gate to source voltage is added to Vx if a gate to source voltage is added to Vx. If a gate to source voltage is added to Vx, then the required Vb can be obtained. This is a very important point to be noted. Now, I would like to add a gate to source voltage to Vx to get the required value of Vb. So how it can be done? Another diode connected device, another diode connected device. You know what is the meaning of diode connected device? To ensure that the MOS device is always operated in the saturation region. Another diode connected device is placed at M0. Look at this diagram. Now you may understand why I have drawn this diagram in this frame. Another diode connected device is placed at M0 in series with M1. You can see that in the diagram, M1, thereby generating a voltage Vn. Now I am using M0 in series with M1, where I am going to generate voltage Vn, and here this voltage is nothing but VGS naught plus Vx. VGS naught plus Vx. That is understandable, right? So Vn is equals to VGS naught plus Vx. Now we have to make a proper choice of M0 with respect to M3. I will write that diagram. A proper choice of M0 with respect to M3. So please see here, I have got M0 in this frame and I have M3 in this frame. A proper choice of M0 with respect to M3 yields a proper choice of M0 with respect to M3 yields VGS naught equal to VGS3. Now we have the similar or symmetric transistor selection as long as the M0 and M3 is concerned. So if you properly select M0 and M3 or M0 with respect to M3, we will get VGS naught equal to VGS3. Now connecting node N, please try to understand this, connecting node N to M3 or the gate of M3. So we get, please check here, this node N is being connected to M3. It is being connected to M3. So how would you connect that? So anyway, the connection diagram I will show you just now. I will write in the next frame only because this is full. Connecting N to M3. So I will redraw the diagram now with all these things. I have this as my current source here, followed by M0, and this will be my node N. So this will get connected to M1. Of course, both these are the diode connected. I will just connect a diode like this, or the symbolic representation of connecting the diode. So this is connected to ground. So now this is my M0, this is my M1, what I had drawn in the previous frame, M0 and M1. Of course, I have I reference as well. This is my I reference, and this is VDD. So this node is N now. So what is being told here is I have one more transistor here, which I had shown in the beginning, which is the output transistor, whose current is required to be controlled with respect to the reference current. And from this I had connected one more transistor, something like this. If you remember the first frame, this one, this diagram you can see. So now what I am trying to do here is I am connecting one transistor M0 here, that's all. Okay, so now this node N, you go here, connecting node N to M3 gate, or gate of M3. So this I am going to connect it here, and I have to mark this as M3. This would be my M2. This is the basic transistor whose output is required to be connected or controlled. This is P, and this is my I out. This is my I out. Now look at this diagram. I reference P. So this gives me the complete cascode current mirror circuit. This gives me a complete cascode current mirror circuit, right? So what I had said here, so a proper choice of M0 with respect to M3 yields VGS0 equal to VGS3. So in order to do so, I am connecting the node N to the gate of M3, the diagram of which I have drawn here. So this implies VGS0 plus Vx, VGS0 plus Vx is equal to VGS3 plus Vy, VGS3 plus Vy. Please check this. VGS0 plus Vx is equals to VGS3 plus Vy. So if I choose the transistors or the MOS devices in such a way, the ratio of the width to length of the third transistor to the ratio of width to length of the first transistor is equal to this ratio of second transistor to first transistor or first device, then I can have VGS3 is equals to VGS0. So when VGS3 is equals to VGS0, I can have Vx is equals to Vy. This is what we wanted to have. Select the third transistor to first transistor or zeroth. Okay, so this is M3, this is M0. This ratio and this ratio should be proportionate, right? So select these transistors in such a way that the ratio of W by L3 to W by L0 should be equal to W by L of 2 to W by L of 1. So that will make sure that your VGS3 is equals to VGS0. When VGS3 is equals to VGS0, my Vy will become equal to Vx. See, whatever the variation that used to take place here, that is in our earlier diagram, we had VDS2 here. This was VDS1. So without the other transistors in our conventional current mirror circuit, right? Even though VDS1 is equals to VGS1, which is equals to VGS2, but your VDS2 was not equal to these values. So therefore, whatever the variations that you are going to have here, that would have prevented the entire circuit to copy the output current exactly as per the reference current, right? So that is when you consider the effect of channel length modulation. Now what we are trying to do here is to suppress the variation in the voltage here. We wish to have Vy is equals to Vx. So in order to make sure that Vy is equals to Vx, we are using two more transistors. One is M0 and another is M3. So the ratio of the third transistor to zeroth transistors in terms of its physical parameter, if chosen equal to the ratio of W by L of the second and first transistor, then it is possible for us to have VGS3 is equals to VGS0, which will make my Vx is equals to Vy. So when my Vx is equals to Vy, that is where I had started with. So my I out becomes exactly equal to I reference. So this particular problem we are going to face, especially in the current mirror circuit. There this potential and this potential are no longer equal. Now if I want to bring this potential equal to this potential, I add some other things here. That's what I had been telling, and that is called as the cascode current mirror circuit. This is what you are supposed to see here. This is called as the cascode current mirror circuit.